I'd just like to say hello and welcome everyone for coming on to this first webinar hosted by the MTC Training and the National Centre for Additive Manufacturing on the subject area of powder management for additive manufacturing. I'd like to introduce myself. So my name is Colin Bancroft. I work for the Advanced Manufacturing Training Centre, part of the MTC. And my colleague Jason Dawes, who's going to be delivering the webinar today in partnership with myself. I'd just like to remind you all that the session is going to be recorded today, so it could be viewed at a later date. We'll be taking questions throughout the webinar, but if you could use your chat function, which can be seen at the bottom of your screen, you can click there, type your questions in, and then we'll have some time at the end of the webinar to respond to those questions. If there are any questions that do run over the allotted time, what we can do, we can take those away and then respond to those with appropriate answers via email at a later date. So what I would like to do, I'd like to introduce Dr. Jason Dawes, who's our Technology Manager for Materials Engineering at the Manufacturing Training Technology Centre. I'd like to hand over to Jason.
Good afternoon all. Colin, hopefully you can hear me.
I can hear you fine, thank you, Jason.
Yeah, excellent. Okay, apologies, I wasn't sure how to unmute myself for a minute there. Yeah, so good afternoon everyone. I also hear there are people dialing in from overseas as well, so good evening and good morning if you're calling in from further afield, whatever the time may be. I think because I'm the meeting host, I'm guessing that people are probably going to be coming through the whole time. Colin, I'll just have to keep admitting them as they come through, right? You can't take over that capability for me, can you?
I think Guy's going to be looking after that for us.
Right, okay, so hopefully that'll stop popping up, or not. Okay, well, we'll make a start anyway in favour of time. Yeah, so I don't know if anyone used to get that stress dream, you know, the night before a big presentation where you dream you're about to do the presentation and then suddenly you realise that you forgot to get dressed this morning. I suppose the good thing about COVID-19 right now is that's not an issue that we have to worry about. So that's one thing less to worry about when we're doing presentations, because now obviously everything has to be done by the internet. And I guess the good thing is we can't see the audience that we're representative either. So in my mind's eye, I can imagine everyone making a ruckus laughter at my my very good introductory joke instead of stunned silence. But anyway, in favour of keeping this as an R-rated presentation, I can assure you I am fully dressed. So, as introduced by Colin, I'm going to go through the next maybe 40 minutes or so, giving you an overview of powder management in additive manufacturing. Hopefully, give you a flavour for why it's important and why you certainly should be taking it seriously. Now, 40 minutes. Obviously, this is a very large topic to cover. 40 minutes is not going to be enough time to cover everything. So if there are lots of questions at the end of this, as Colin said, we are going to be taking questions throughout, and we'll answer as many as we can at the end of the presentation. And then any left over, we'll try and send out an email response to those questions that we don't get to. So without further ado, let's work on the presentation. So good timing. So additive manufacturing then, what is it? So simply put, or at least simply put as the media puts it, it is a manufacturing technology that effectively we come up with an idea of a part, a design of a part that has infinite complexity, can't be built in any other way. We effectively design a CAD of this part, and then we just click print, put our CAD file into our machine, put some powder into the machine, click print, and layer by layer, our part is built. And then at the end of the process, we have a final product of infinite complexity and of any product we simply desire. Now, for those of us that are initiated within the AM community, we know this simply not to be true. And for those that are maybe just entering into the AM market and maybe don't realize the complexity, I'm afraid I'm about to burst your bubble, because this is simply as far away from the reality as possible. Sorry. So what additive manufacturing actually involves is an awful lot of steps in order to get the part right. Because we're designing parts of very complex features, we're going to need a very robust inspection plan. The harder the design, the more difficult it's going to be to inspect and validate. The part does not come out finished. When we have a part post AM, there's a lot of machining steps required. We've got to recover our material, we've got to remove support structures, we have to finish it. So there is some level of machining to do after AM. We also have to identify the appropriate melt strategies to melt the material properly and get a good microstructure free of defects. There's a lot of things we have to do up front around the design. It's not just the design of the part itself, but also the support structures that need to go around it. Unfortunately, powder beds are very poor conductors, so heat builds up in the part. If we want to get that heat, we need to have a sensible amount of support structure around it to take the heat away from the part, but also to appropriately anchor it. So there's a lot of considerations that need to be made at the design stage. And then, of course, as the topic of this powder, there are lots of considerations that we need to make when it comes to powder. So you'll see a lot of these steps involve something that we have to do with our powder material. Now, obviously, the scope of this webinar today won't cover all of this, but I think, fortunately, over the next few weeks, MTC and the AMTC are putting on a number of webinars, which I believe will cover the whole process chain of the additive manufacturing process. But today, we're going to focus just on these powder handling steps. So why should we care about powder then in the first place? So commercially, if you actually think about the powder itself, we're buying an atomized material, which in itself is more expensive than buying billet material. So the material itself is very expensive. When you actually run the numbers on this, it can, in some situations, some scenarios, it can make up to a third of the overall production cost is just simply buying your powdered material. Now, additive manufacturing is often billed as a material sparing technique. What that means is that we only use the material that we need in order to build our part. So if you look at things like negative manufacturing, where maybe we can lose 20, we can have 20 times more material to start with than we make parts, we get a buy to fly of 20 to 1. In AM, because we're building parts much closer to net shape, we can use a lot less material. But when you think about what additive is doing, you're spreading an entire chamber full of powder and only making a small amount of that volume that you've spread into actual parts. So the ratio of powder used to part built can be just as bad as negative manufacturing. So in order to hit that material sparing criteria, in order to make the business case work for AM, we have to be able to reuse the material. But every time we use it, how is the powder changing? Is it still suitable for the process? Is it still applicable to use in my next process, or do I need to throw it away? So we've got to be able to understand that. And then, of course, the supply chain needs to be validated. There are lots of different suppliers of metal powders, and not all materials are made the same. Some materials may work very well, but another supplier may make a material that doesn't work as well for your process, depending on which one you're using. So you've got to understand your supply chain. You've got to be able to validate that and know that where you can get your material from is going to work in your process. Technically, well, what's additive manufacturing? It involves several thousand layers of thinly spread powders. If every layer isn't consistent, then effectively that gives us thousands of chances to get it wrong. So if one layer has incomplete surface coverage of the layer, let's say you've got no powder in a particular area, that's going to be a defect that's going to carry on into your part. And therefore you're going to get defects in your part. So powder consistency is absolute paramount in the process. Because we're reusing the powder, like I say, we don't know if it's going to be the same every time we use it. It may degrade or change in some way. Therefore, we need to be able to manage that process. We need to be able to revalidate our material. We need to be able to understand if it is out of spec, how do we bring it back into specs? We've got to be able to manage that whole process. And of course, the quality of the powder directly impacts part quality. It's the old adage, put rubbish in, you get rubbish out. We've got to make sure that the powder we're putting in is right for the process and is going to give us parts of the right quality. So there's a lot of reasons why we should be caring about the powder. It's not just this grey material that doesn't matter. But what can go wrong with powders? There are a lot of challenges with powders for AM that can come from just the inherent way the process is run, the fact that we're recycling material, the fact that we're using material which is inherently, titanium for instance, is quite an excitable material. It is flammable material. It's aluminium. We've got materials such as nickels, potentially hazardous to health. So there are a lot of challenges when it comes to AM powders. So some of the things that I believe we need to be concerned about are things like contamination. Contamination is really hard to control. If we're getting bits of our machinery, for instance, surface, parts of the steel surface are breaking up and coming into the material, that's going to contaminate it. If we have other materials that we're handling in the area and they cross-contaminate, that's going to contaminate our powder. That might not be suitable then to reuse in process. We've got to worry about contamination. Process incompatibilities, like I've already said, if the material's not appropriate for your machine, your part, you're not going to get a good process and a good part at the end of it. Health and safety, obviously, is a huge risk and something that we absolutely need to be getting right and making sure we're doing it properly. Powder part ratio, like I said, it can be as bad as, if not worse than negative manufacturing if we're not able to recycle powder. So we've got to make sure we know how we can do that well. And then the other thing is poor powder management. If we don't know the history of our material, then we really shouldn't be using it, because we don't know if it's still good for use, if it's been handled in the right way, if it's been exposed to unfavorable conditions that might have degraded it further. We just don't, if we don't know the history of this powder, and that can get very complicated. If you've got a powder that's been recycled over 50 times and multiple powders like that on site, it can get very complicated how you manage that material. And if you don't have that history, then you don't have a process. So there's lots of challenges when it comes to AM powders. So maybe just to drive home a little bit, if we just look at a very basic overview of any process that we're running, our parts that we make are obviously going to be inherent of the material that we put in there and the way in which we run the process. So if we don't really know what we're putting into the machine in terms of the powder, and we run in a fixed process window, then we can't really hope to control the quality of our properties. It's going to be variable, it's going to be unknown. So what we need to be in is a position where we have a powder which complies with an adequate powder specification. And then that way, when we know that our powder conforms to that specification, we can run our fixed process window, and then we can fix component properties within a tolerance. So there's a lot of questions then that we need to start asking ourselves about this input material. So firstly, I've said it a few times, if I put rubbish in there, I'm going to get rubbish out. If my powder is not compatible with the process, it's not going to work. So the first thing I need to know is, well, how does my powder properties influence the AM process? What does a good powder for my process look like? I then need to worry about my batch to batch. Am I getting the same material every time I order a batch from my supplier? And should I ever need to switch suppliers, do I understand the level of variability between one supplier to another? Do I have a good handle on that? Because I'm reusing my powder, I need to understand, well, okay, how does the AM process affect it? Am I going to pick up oxygen, interstitial oxygen, for instance? Am I going to pick up contamination? Is my particle size going to change? I've got to store the powder at some stage. Well, how's that going to affect it? Does it matter if I store it in ambient conditions, or if I store it in an external shed outside, which is maybe not controlled? Or does it need to be in an area where it's inert and temperature and humidity is controlled? And then, well, what can go wrong with it? FOD, so foreign object debris or contamination. What are the things that can happen to the powder whilst it's on site that are going to degrade or detract from the quality of that? And of course, in order to answer these questions appropriately, we need a robust powder management process. So what is powder management? So effectively, we see powder management as being a framework to enable full material traceability and quality control of powder feedstocks and manufactured components. And so a good powder management process should enable us to answer these three fundamental questions. What has happened to my powder? Where's it been? How many times has it been used? What machines has it been used in? What processes has it gone through? Has anything happened to it that may lead me to believe it's no longer in specification? Like, for instance, was it used in a machine where the oxygen content raised above a threshold, and therefore I might have some high levels of oxygen in my powder? I want to know what's happened to my component. So the component I've made, what the powder that was used to make it, like what's the history of that, and then what's happened to my equipment. When I've used the sieving equipment, for instance, has the sieve screen broke? And I might find that out by looking at doing a quality control check on my powders, and I can say, oh, something's happened with my equipment. I need to have a look at that. And so why implement powder management? I believe it would be clear to everyone right now why we should be implementing powder management, but just maybe to drive it home, really, there's a term that's used in the aerospace industry, ALARP, as low as reasonably practicable. Where a powder supplier was contacted by someone they've sent material to, and this user of the powder has lodged a complaint. Your material that you've sent us is contaminated. Now, when they did a failure investigation to understand what happened, actually there was nothing wrong with the powder supplied by the supplier. The issue was actually with the user, because they weren't using dedicated machines. As in, they weren't using a machine dedicated to a material type. They were switching materials from build to build. And what actually happened was the previous time they used that machine, they hadn't cleaned it out properly. And so when they put this new material into it, it became contaminated with the previous material. And so they ended up with some unexpected component failure. And that's really important that we've got to be able to minimize that as much as possible. The other one, it happens. Human operators at the end of the day run these machines. Material misidentification. It's about understanding, making sure or minimizing the risk as low as reasonably practical of putting the wrong material into the wrong machine or the wrong process. And then the other one is this concept of lack of traceability. As long as I have good document processes and I keep track of what I'm doing in my powder, I can be reasonably confident that I have a good level of traceability of that material, and I know how it's been used and what might have gone wrong with it. And so what the powder management cycle looks like. So this is what we implement at the MTC. And again, with the time that we have available, there's not enough time to go through all of this. But the step by step, we need to validate our material. We need to receipt the powder. Now this is very basic, powder receipting, but it's so important. You know, it wouldn't be the first time that we've ordered material from a supplier and that material has been the wrong material. For instance, that's happened to us before. It might have the right labeling, but the wrong material inside the container. It might be arrive in a damaged container. If the container is damaged, how do I know the powder inside is going to be good? For instance, it may have been exposed to elevated humidity and temperature, and therefore the powder inside may have degraded. So powder receipting becomes very important. Did I get what I ordered? Did I get it in a good condition? And did I get the amount that I ordered it in? Quality assurance, again, is so important. But the reason quality assurance becomes so important, it's not just about when I first order the powder and first receive it, it's about when I use it afterwards. The powder supplier only needs to get it right once, but as an end user of AM powders, I need to be able to get it 10, 20, 50 times, however many times I'm going to use it, I've got to get it right. I've got to make sure the powder is good to use still. Powder storage and segregation, again, it's about reducing that risk as low as possible, having dedicated areas for certain material types, having the appropriate storage conditions, whether that's humidity and temperature controlled, whether that's ambient conditions. Of course, at some stage, once I've stored and I've quality assured my material, I'm going to use it, I'm going to handle it, I'm going to recycle it, and I'm going to track what's happened to it. I'm going to get all of that documenting. And then, of course, that's a cycle that keeps going round and round and round until at some stage, I'm going to fail quality assurance. I'm going to have to dispose of my powder. And of course, each of these stages, we've got to make sure we're doing it safely. So health and safety needs to be considered throughout. So supply chain validation. Now, one of the things that I always like to preach about AM powders and the supply chain for AM powders is that the powders come in many shapes and sizes, depending on the process that was used to make the powder. And in most cases, even if the same process is used, depending on the supplier of that powder, I will get either very or subtly different powder properties. And that's going to affect things like bulk packing, flow properties. It's going to affect effectively the way it works in the process. Now, obviously, there's not enough time to talk about all the different atomization processes here, but it's really important that you understand what is the right atomization process for my material. So some of the very pertinent things that you need to consider. Am I using a nickel superalloy, for instance? If I am, I probably want a powder that's been atomized via argon rather than nitrogen. If I'm using titanium, I probably want to be going to a supplier that uses IGA, where you're using an electrode induction gas atomization, rather than a supplier that's going to use a crucible. So there's lots of things that we need to consider. We need to understand the supply chain and how it affects our material. Now, when we look at the actual AM process, so how's powder handled in the AM process? Well, there's 4 things during the actual process that we need our powder to do. So the first one is storage. Clearly, at some stage, we need to put powder into a machine. And of course, anyone that's ran an AM process, you will know they're not exactly fast. It could take days. It could be 3 to 5 days to complete a build from start to finish. So during that time, we need to make sure that powder is stable. We need to make sure there's enough of it to start with. So is the bulk density sufficient that we can pack enough material into this hopper that we can get through the whole of that build? Is there going to be any change, like particle size distribution? Is there going to be any segregation in that hopper during that time? Is there going to be any time consolidation, which may mean effectively that whilst I get good dosing to start with, does it degrade over those 5 days? There's a lot of things that we need to consider effectively. At some stage from that storage, we need to dose our powder into our machine. We need that to be consistent every time. Every time we need to dose the right amount. We need to dose a consistent particle size distribution against a no segregation. And it has to be equal across the face of our spreading device. So very different behavior to static now. We need to go from this static condition in a hopper now into a flow condition. At some stage then, after we've dosed it, we're going to need to spread it across the bed. Again, flow becomes really important, size distribution important, morphology starts to have an effect on things like flow. But effectively what we're trying to do now is have a very even coating of powder across this platform, this build platform. And we need to do that, like I said, every time, which is thousands of times. So again, very different behavior that we need from our powder compared to dosing or compared to storing it in a hopper. And then eventually, ultimately, we want to melt that into a part. And that's where things like chemistry are going to become important. Is the chemistry correct? Is it clean? What I mean by clean is it free of interstitial contamination, such as oxygen, for instance, or at least within the right spec? Or is it free of foreign particulates? And then we might be worried about porosity. Is there porosity within the particle that when it melts, it might cause issues? And again, bulk density. So when I've spread it, have I got a consistent bulk density? Is it dense enough that I get good stability of the part and I don't get too much shrinkage when it melts, for example? So lots and lots of different things that we want our powder to do. And this is just inside the machine. This is before we even consider how we get the powder into the machine and out of it and all of the equipment we have to handle it through in order to recycle it. So we demand a lot of the powder in terms of performance. And if at any stage this goes wrong, it could be as simple as my powder doesn't dose. And that happens. I've seen many examples where we've put a powder into a machine and it doesn't dose. In that case, that's in effect, that's a catastrophic failure, right? The machine just isn't going to be able to build. And these are things that happen. So we've got to be able to make sure that we understand how our powder, what powder we need in order to do all of these things efficiently. And so how do we do that? Well, unfortunately, powders are quite complex and there are a lot of things that we need to measure. So we tend to talk about 4 levels. So you've got our particulate properties. So this is the thing like particle size and its distribution, particle shape, internal porosity, of course, the energy. Then those particles obviously are going to form an assembly, a bulk. So then we're worried about how those behave in that assembly. So packing becomes important. So how do they pack? How do they pack under a loosely poured condition? How do they pack under a tapped, stress-induced condition? How do they flow? How do they flow out of hoppers? How do they flow in the spreading device, for instance? These are all things we start to worry about. Then, of course, there's the chemistry. I always like to say, no matter how good a material flows or how good the morphology is, of course, we're never going to choose a material unless it has the right chemistry. So that's fundamentally, it's the most important thing. Is the chemistry correct in terms of its alloy composition, but also in terms of the interstitial elements like oxygen and nitrogen that obviously will have an effect on mechanical properties. And then there's cleanliness, which is a lot harder to identify. There are no standardized techniques for this, but it's important nonetheless to understand, is our material clean, or is there something in there which, if it forms the final part, is going to be detrimental? Now, in the MTC, we have a exceptionally well-equipped lab, and we have access to all of this equipment. But clearly in industry, that's too much of a burden. The cost of the lab is too expensive. The expertise needed to run the lab is vast. And so what we as a company are trying to help industry achieve is something called the minimum descriptor set. So it's understanding what are the key process variables, the KPVs of the powder, which have the biggest influence on the process. And that's what we're trying to get to. So we cut this entire whole host of experimentation down to just a few key parameters. And that's the golden egg that we're trying to get to, is to understand, well, what are the things that matter most rather than everything that we can measure. But maybe just to give an example of where powder quality does start to give an impact. So a very, very brief case study. We have two suppliers, obviously anonymized here as supplier X and supplier Y. It might become apparent just from these SEMs. Apologies, I think they are quite compressed, so the image quality is not coming out particularly great. But take it from me, the supplier X is somewhat more irregular. It's a bit more satellited, whereas supplier Y is a bit more spherical. So that has impacts on things like flow and packing densities. But what's really interesting about these two suppliers is supplier X tends to have more instances of particles with pores. So you can see that in the second SEM image at the top. You can see an outline of a grey particle, but then with a black void in the middle. So that is a pore inside a polished particle. Now, there seems to be a complete absence of those porous particles in supplier Y. Now, when we build parts, I don't want to try and say this is cause and effect, but when we build parts on the same machine under the same conditions, we see very large differences in porosity of the part. So with supplier X, you see substantially more pores within the microstructure than you do with supplier Y. That's not to say that supplier Y in this scenario is better than supplier X. It's just that we have the right processing conditions for supplier Y, whereas supplier X we might not have. We could probably improve that microstructure substantially by modifying the melt parameters. But I hope what that does is gives you a feel for the fact that just because it's the same chemistry doesn't mean it's going to process the same. This is why it's so important we understand that link between our powder properties and how to process the powder in the machine. It's to avoid issues like this. A straight swap, no changes in parameters, we get very different microstructures, very different part properties. So on to powder reuse then. So why is this so important? So in the process, there are several things that we want to be concerned about. So the first one is a phenomenon known as spatter, weld spatter. So I already mentioned that powder beds themselves are very poor conductors of heat. So what this means is that actually when we melt the powder particles during the process, because we're not releasing that heat from the melt pool, what can happen is the melt pool can exceed the boiling point of the material. And if that were to happen, we get this, where effectively we get particles ejected from this melt pool. And you can see them, they look like mini firework displays if you ever watch an SLM, a laser melting process in operation. Of course, what these particles are, they're molten, so they're very, very hot. So any residual oxygen in that container, those particles are going to pick them up. But also, in a similar way to the atomization process, those molten droplets, if they come in contact with anything such as a surface or other metallic particles, they're going to have deformed geometries when they freeze, when they reharden. And if those are too large to be taken, if they're too small to be taken out by the sieve, then those irregular particles will then be present in your powder after you've recycled it. So you're going to have potentially bad morphology and locally high oxygen content in these particles. So that's bad news for your recycled material. The other issue we have is something known as the HAZ, the HAZ, heat affected zone. So the heat affected zone is the powder immediately adjacent to the melt piece. So this is powder that's not melted, but it is exposed to elevated temperatures. And so because it's exposed to elevated temperatures, again, there's the chance that it can form agglomerates and sinter with surrounding particles, but there's also a chance that it can pick up oxygen from the environment. So again, locally, we're going to have higher levels of oxygen on particles. The heat affected zone, of course, is going to depend entirely on the type of part that you're making in terms of, say, the surface area of the melt, but also the processing parameters in which you're running your process. So that can be more or less affected. Now, the third one, and if you're not familiar with electron beam melting as a technique, you won't have come across this, but is preheat sintering. So in electron beam melting, for all sorts of reasons, we have to pre-sinter the material in order to something called the smoke, effectively where you build charge up in your particles and they basically repel one another and you get a big puff of smoke, of powder particles flying up into the air. Down the system, it's bad news. So you have to sinter. But of course, what that sintering is, it's a soft melting. So you're not fully melting the particles, but you're heating them up sufficiently that they form necks and sinter with adjacent particles. Now, because the sinter area in EBM tends to be quite large relative to the part, coming back to that whole process economics, you've got to be able to reuse that pre-heat sintered powder. So you break it down as part of the recovery process back into its individual powder particles, which then get put back into the machine. Now, again, because you pre-sintered, there's chance that raised temperature, therefore higher oxygen content in the particles locally, and potentially, because you've sintered, potentially there's going to be a morphology distortion, and so again you're degrading your morphology of your particles. So these very nice spherical particles are no longer as spherical. Is that going to affect the way they flow and pack in further builds? And so when we look at powder degradation, some of the things that I think we need to be most concerned about, I think there's two of them. So the first one is interstitial contamination. So the graph shown on the slide on the left as you look at the screen shows real, again, it's fully anonymized, but real data captured at the MTC, showing a titanium powder, which initially is within the ELI grade. So that's the extra low interstitial grade for titanium 6.4. So spec limit of 0.13% weight oxygen. Now what we can see is as we recycle and reuse the material, the oxygen content is increasing to the point where eventually, sorry I've covered the numbers up, but it's 5, 10, 15, 20, 30, 35, roughly 35 builds, it eventually transitioned past that spec line. So this material, if we needed a part that was ELI, this material is no longer suitable. We'd have to scrap this material at this stage. Now what's important is that if this is a linear trend, as it appears to be, and this would happen whatever the starting condition, clearly if we bought material that was at 0.1, it's still ELI powder, but clearly if it picks oxygen up at the same rate, we're not going to get very many builds at all before it transitions. So that starts to bring in, again, that issue of supply chain validation. If I need an ELI powder, who supplies me the lowest starting oxygen content and consistently provides it at that? Because if I base my business case around, okay, I can accept 35 builds, but every other time I buy a batch of material, I only get 5 or 10 builds out of it, I'm clearly not going to stay in business very long. So again, comes back to that supply chain question. It's really important. Do I know who my suppliers are that provide me the powder I need? The other issue, of course, is foreign object debris. Again, examples of real life parts built at the MTC. We can see this part here. lots of red dots on the image. Each of those red dots, this is an XCT image for those that aren't aware, each of those dots represents a high density inclusion. So a particle which is of higher density than the surrounding matrix material. They turn out to be tungsten. This particular part was built out of a material which from source had elevated levels of tungsten particles in it. So again, it's a supply chain issue. Do I know which suppliers can provide me with clean powder in the first instance? But even if it didn't have it at the start, every time I use the powder, there's chances that I could be adding foreign object debris in there. So the two images below represent recycled powders, and they represent they represent foreign object debris that we've found within those powders. So both of these just so happen to have chemistry, that is consistent with stainless steel. Of course, it's been measured using SEM, so we can't guarantee that it's stainless steel, but the elements that are there lead us to believe it's stainless steel. And so that is likely debris from the equipment we've used to process the powder. This elongated one could very well be a part of a sieve. This could be a piece of debris from the. So how do we do powder recycling then, and what are the challenges of that? So we've got a machine, and at the end of a build, we're going to have some remaining powder in our hopper that we loaded to start with. We're going to have the unmelted powder in the build platform, and then depending on what machine we're using, we're probably going to have some overflow container which has powder in it as well. And we need to be able to recover powder from all of these places. So the first thing we're going to do is we're going to convey the material from the process, from all these three separate areas of the machine. We're going to put it into storage. We're then going to convey it to a sieve where, again, depending on the process that we're running, we might have a single sieve deck and only cut out the oversize, or we might have a double sieve deck where we cut out both the oversize and the undersize, and we keep the bit in the middle. Then at some stage, we're going to bring that back to storage. We might take a sample at that point to do some quality assurance testing, and then we're going to load it back into the machine. Now, again, this is a bit divisive. I'm not included it in this graphic. A bit divisive in the industry. We may also blend the powder at some stage, just to homogenize it and mix in some new material. But the point is, at each of these stages, if I'm not careful, I have the ability to contaminate the material. I have the ability to expose my powder to atmosphere, and I have a risk to traceability. So I need to be able to manage all of these. Now, the equipment that we use in recycling, there's lots of hoppers, obviously. There's a hopper in the machine itself, and usually when I decant from machines or from one process to another, I'm going to put it into a hopper. We've already talked about the potential issues with flow there. So the challenge with the equipment is, will I get good flow of material out of those hoppers? I obviously need sieves. Again, lots of challenges with sieves. Am I going to blind my sieve? If my sieves are likely to blind, what can I do about that? What kind of sieving technology do I need in order to get the most appropriate sieving? At some stage, I might need blending units. Again, blending is a whole science in its own right. Worst case scenario is you may as well have not blended in the first place, because actually by blending inappropriately, you can segregate particles. So you might end up with a really particle size segregated material. Think about your cornflake box. When you got your fines, they all sift to the bottom and large sits on the top. So if I blend inappropriately, I could cause that to happen. How is that then going to affect future uses of this material? And then with some of the newer machines that are coming available, there's actually a lot of pneumatic conveying. What's that going to do to my material? Is that going to degrade my material? Is it going to cause any breakdown of the material itself? Unlikely, because it's hard metal powders, but there's a good chance I could cause breakdown of the transfer lines, and therefore degrade my material by putting in contamination. So there's lots of equipment that we use. And again, we need to understand what is the right equipment for my process and for my powder. So it's not just as simple as, I want that one. So powder storage, at some stage you're going to have to store it. And I guess what we're interested in here is, what is the way to store material? So I might want to worry about the actual gas that's in contact with the powder. So I obviously put my powder in a container. What's the gas around it? Does it need to be inert? Is it okay to just be ambient? Do I need to add desiccants to try and remove moisture from the immediate area? So again, this is internal environment that the powder is stored in. Then there's the container itself. Is it okay to use plastic jars, which a lot of powder suppliers use, or do I need metal. What's the right container for my material? And then there's the external environment in which we store that container. Is it okay under ambient conditions, or does it need high level control, such as humidity, temperature control, or even one step further, inert gas control? These are the questions that we need to understand. And again, there's not a one size fits all. It fundamentally depends on the material that you're using and the level of criticality of the part you're trying to build. So there's not a one size fits all here. What the most important thing here is it has to be cost effective. It has to be the minimum requirement to maintain powder quality whilst costing the least amount of money. So it's not appropriate to just apply the highest level of control over storage in every situation, because at some stage it just might be cost prohibitive. So again, we've got to understand what is the right way to store our material. So the last thing I want to cover is a bit on health and safety. Now, health and safety is a bit of a minefield when it comes to metal powders, and that's simply because there probably isn't enough data working with them. So I just want to give you a real example, which is available on, you can read it up on the internet. So it comes from the medical sector. So an employee effectively was using a vacuum to clean up a spillage of titanium powder. Now, the vacuum this employee was using was inappropriate for the job. It wasn't grounded properly, and therefore it was able to build up static charge. And then the static charge obviously was enough to ignite a dust cloud of titanium-64, which led to severe injury of the operator in question. Now, in this scenario, you could say they were lucky, so clearly one person getting injured is not ideal, obviously not. But when it comes to explosions like that, sometimes it's not the primary explosion that's the worst thing. It's often the secondary explosion. So and why that's so important is if you get one explosion, if you have any dust around your facility that hasn't been cleaned well, that can get desettled and then in itself can cause a secondary explosion, which can be much worse because there can be a lot of it. So clearly housekeeping is a major issue. You should keep on top of it. But why this is such an important thing to highlight is, okay, this is clearly inappropriate. The wrong vacuum was used. But when we look at the suppliers, MSDSs, the material safety data sheets that you get from powder suppliers, we've got supplier 1, do not vacuum. There are reports of titanium dust explosion even when using an explosion-proof vacuum. Supplier 2, vacuum or sweep spill using smart-proof tools and explosion-proof equipment. So even within the supply chain, there is some level of unknown and no level of consistency. And I'm not saying I have the answer, it's merely just highlighting the issue that we have to consider health and safety, what is appropriate to do and what isn't appropriate to do with our materials. So something we did at the MTC, and I will just go over this case study quite quickly now. We worked with the health and safety executive, which is part of the health and safety lab. And effectively, we looked across a number of different AM processing sites to look at the level of exposure that our employees are exposed to, because clearly explosivity is one issue, but another issue is a lot of the materials we work with, such as nickel, potentially carcinogenic. So we've got to be able to protect our operatives. So effectively, the HSE came into these three sites, and we put various testing equipment around the lab. So we would put sticky tabs at different locations from an activity. The operatives themselves had personal monitors on close to their mouth and close to where their respiratory equipment would be pulling air from if they were wearing belts. So we could get an indication of the level of particular exposure at those locations. And then we also did personal monitoring. So we did some testing of the operatives' urine to see if they had elevated levels of, materials that they use in AM. And so these are effectively the results for the 3 sites. Now, the good news story, at none of the sites was there a higher level of occupational exposure than than specified in MSDSs. So no one operative was exposed to a level of material that's higher than it should be. But what we did find from the study was that actually the level of airborne particles depends on the task that the operative is carrying out. And so where the worst option, worst tasks were things that involved manual handling of the powder material itself. So whether that was decanting from one equipment to another, or whether that was sampling for the lab, or whether that was doing lab techniques, wherever you are manually handling powder, there is a chance that you can create airborne powder particles effectively. The other good news was in biological monitoring, there was none of the operatives that we looked at that had a level higher than what is considered safe. But there was operatives that had raised levels compared to the general populace. And so we can say that we are doing a good job when it comes to health and safety. There's the level of PPE that we use is good, even if we are overly reliant on it. Some of the endeavors that a lot of the equipment manufacturers are doing, they're trying to develop more sealed units. So sealing the powder away within the machine so that transfer is more automated rather than manual. But I think there's still more that needs to be done in this area, both from users, but also from equipment suppliers. And so it brings us nicely to the end of the presentation then. So just to conclude, maybe just some of the salient points that I've tried to get across. So it's powder management. I hope you can all appreciate now that it's an essential activity, but understand why. So if you missed it, the three things that I think powder management is essential for is unexpected component failure, material misidentification, and lack of traceability. All powders are not made equal. So I can go to 5 powder suppliers and I can get material of the same chemistry, all material that hits a chemistry spec. But it doesn't mean that everything else about those materials are going to be the same. It doesn't mean that the starting level of oxygen, for instance, will be the same. Some might be low, some might be high. It doesn't mean the morphology, the size, the flow is going to be the same. Therefore, I can't expect any material that fits a chemistry spec to also work the way I expect it to in a process. It's more involved than that. Powder recycling, of course, essential. If I want my AM process to work economically, I have to be able to recycle the powder. I can't buy this expensive material and throw it away after one use. I've got to recycle it. So I've got to be able to manage that process, and I need to be able to optimize it. And of course, health and safety, I hope this should be clear to everyone anyway, but health and safety in metal powders absolutely needs to be fully understood and controlled to prevent injury to personnel, but also to prevent destruction of property or equipment. And I think this is an area that the whole industry needs to come together and work on to solve, because at the moment it's not consistent across suppliers. And so on that, I'll hand back over to Colin, who can talk us through some of the other things that we have available at the MTC if you wanted to find out more information.
Thank you, Jason. I hope you found that topic rather interesting. It was good to point out that I think throughout the presentation, the importance of understanding the powder management process and also how to handle powders appropriately. So I work in the Advanced Manufacturing Training Centre side of the Manufacturing Technology Centre business. And what we've done, we've worked collaboratively with the National Centre for Additive Manufacturing and utilised the skill sets from the specialist engineers to help design training solutions to support industry in the adoption of additive manufacturing, but more importantly, the fact that they can adopt additive manufacturing in the safest possible way. So as you can see on your screen at the present, we've got our 2 powder handling courses, one on powder handling, which is a 2-day course, and it's looking at applying best practice from receipt right the way through to disposal, looking at the safety considerations at each stage, and then further and more in-depth information on that particular course can be found on the website, and there'll be a link to the website towards the end of the presentation. Likewise, with best practice in powder management, what we wanted to make sure that we're doing here is justifying the rationale for a powder management system. And hopefully that's been made quite clear throughout today's webinar presentation, looking at what health and safety documentation is required and what management strategies need to be put in place to ensure that you know what powder is being used where, what machine it's going into, so then you can start to determine the build quality of the parts that you're trying to manufacture. And if you could just flip to the next slide, please, Jason.
Of course, yeah.
And then what we've also got is a specific online course around additive manufacturing, health, safety risks, and mitigation. So what this is for is to look at applying the best practices and safety guidelines to the AM equipment that's being used, the materials themselves, and also the post-processing activities once the build has happened. And then if there are any eventualities and how to react to any specific safety related incidences that can occur with the additive manufacturing processes. Again, additional information can be found on our website that can be seen below, or you're more than welcome to contact me directly, and then I can point you in the right direction of which course is probably most appropriate to your AM adoption journey. What I'd like to do now is just go through some of the questions that have come in, so I can, and I hope Jason's on hand to answer some of these questions. So one of the first questions that's come in is from Ina, and it's for you, Jason. Are the measurements of the powder degradation published anywhere?
There are a number of white papers out there, yes. So there are some conference proceedings that we would have wrote up ourselves, and there are definitely, so that work that I presented on there was done in collaboration with Renishaw. So Renishaw will have white paper notes on their website, I believe, that's available. And there are other studies that have been published elsewhere. If anyone's particularly interested in getting hold of those, I guess we can probably share them, can we? I mean, they're freely available, public domain, Colin. So.
Okay. And then we had some questions came in prior to the webinar actually taking place as well today. And again, one for you, Jason, is how do we know when a powder reaches the end of its usable life?
Yeah, okay, it's a good question. So generally speaking, what we would want is up front to have a specification for our material. And so the things that I usually see, the reasons I usually see for a powder coming out of spec would be because something like interstitial oxygen going above that level. So like we discussed on the recycling case study, when we use a titanium material, for instance, oxygen content does increase over time, probably more due to the events such as spatter and heat affected zone rather than general pickup from ambient conditions. But once that oxygen gets too high, that's certainly time to put the powder away, stop using it. But the other thing that we have to be careful of is does anything exceptional happen during the process? So I've seen it before where certain machines will have an air sheath that goes across the bed of the powder, so she'll have like an argon flow stream across the powder bed. Now, if that's not set appropriately, what you can do is you can preferentially take a load of fines off the surface of the bed, and what that does to the powder is that actually when you get it back out and you look at the size distribution, you'll have shifted it and not made it coarser, but because you've cut the fines out, you've lost that fine tail, and therefore that powder is now it's the wrong size distribution, so you shouldn't really be using it because it might not perform the same. The other thing is, of course, you might have elevated oxygen content in your machine. So again, that's going to accelerate oxygen pickup compared to normal operation. And then the other thing, of course, is contamination. If you get any level of contamination in there, whether that's debris from equipment or whether that is cross-contamination, that's probably a sign that you should stop using it because it can be very difficult to remove that contamination.
Excellent, thank you. I think there's another question that's came in from Laurentiu. I hope I've pronounced that correctly. Can a printed part be recycled?
Well, that's an interesting question, actually, a printed part. So there are a number of atomizers out there that are looking at recycling pre-made parts. So it's more they were looking into the remelting of support structures, because support structures are obviously, but post-build, they're effectively redundant. They obviously serve a purpose, but they're redundant post-build. And actually over the life cycle of a powder batch, that can be a sizable amount. So I know there are atomizers looking at repurposing used melted material, but in terms of actually successfully selling that into the market, I'm not so sure. I know other industries, they do use recycled parts, so I don't see why it isn't something that we could see more of in the future.
Excellent. And then there's Parry has just asked for coming with another question. Is there any guidance for future on single material systems with powder recycling built in? As an example, Ren AM500 or AddUp systems.
Yeah, it's a good question. So these machines are really interesting. So for anyone that's not aware of what those machines are, so effectively they have their own internal recycling systems. So at the end of a build, automatically the spread powder is taken out of the build platform, pneumatically conveyed to a sieve, sieved in situ, and then put back into the hopper. So the powder itself never actually comes out of the machine, so it's always kept under inert, temperature controlled environment. So clearly from the quality perspective of the material, that is potentially, it's a very good thing. But some of the challenges that I am aware of is, firstly, how do I validate my material? So the whole point is the powder never comes out of the machine. So how do I take a sample and validate that it's still in spec? The second thing is it becomes very difficult to maintain that level of traceability. So the question is, how do I, if the powder is continuously recycling around, how many times has it been used? Like, can I say that with any level of confidence, how many times it's been used? So what proportion of that powder is used? What proportion of that powder is new? So there are a number of challenges. The MTC through the National Centre is actually looking at doing some recycling studies on these machines. So they are relatively new to the market. It's something that I personally don't have a lot of experience with, but we have a Ren AM in the National Centre now, and it is something we're starting to look into. So at the moment, I don't know if I've sidestepped your question. I maybe put out more challenges than answered the question, but I think at the moment it's still an open space to understand actually what is the best way of using these machines. It's a very good question, and one that we're certainly looking into, presently.
Sorry, I think we've got a chance just for one final question that's just come in. It's from Nebraska. May I know the best ways of checking the quantity of a powder's main alloying elements in left out powders, for example, the V and the AL in a TI6AL V4 powder? 4V powder.
Okay, so if I've understood the question properly, so what chemistry techniques are available for measuring alloy composition? So we at the MTC, we use something called inductively coupled plasma optical emission spectroscopy, so for short ICP OES. Effectively what that is as a technique, you take your metal powders, you dissolve it in a mixture of acids. So usually it's like hydrofluoric, sulfuric acid, and nitric acid, I think it is. Effectively, you basically digest it into its constituent elements, and then effectively you pass it through a plasma torch, and through spectroscopy, different elements give off different wavelengths. So each wavelength is unique to a material. So what you're doing is you're measuring the wavelength of light given off by the different materials, and of course the intensity of that wavelength depends on how much is present, and that gives you a breakdown of, if it was titanium 640, it gives you a breakdown of your aluminium, your vanadium, your iron, and any other trace elements that might be there, and you can use that as a way of validating material. There are other techniques available, but that's the one that we use at the MTC in the National Centre, and that's the one that I'm most familiar with. So hopefully that answers the question that you were asking.
Excellent. So what I will do now is conclude the webinar series. I'm just conscious of the time. So if there's any further questions that come in, please feel free to contact Jason or myself directly, and we'll be sending out our contact details to you all. Hopefully you've enjoyed the presentation today. What we're also going to be doing is providing all registered attendees today with a 20% discount code, and that will be coming out to you via email for any future of our additive manufacturing courses, and that can be used for both online or our face-to-face delivery when we're back up and running to deliver face-to-face training. But we're also in the process of adapting some of our face-to-face training to be delivered via live streaming at some point, and we'll keep everybody updated of the updates on that as well. Hopefully you'll be registering for the next webinar in the series, which is going to be designed for additive manufacturing at the same time next Wednesday. Thank you all for attending. I hope you really enjoyed it. Thank you very much.